So in the last lecture, we were looking at the theorem of the theorem that states that a language is context free if and only if some PDA recognizes it. So we broke it into two parts. One is if we can convert the corresponding CFG into a PDA. So that is the first part. And if we can convert the corresponding PDA into a CFG, if we can prove both these parts, then we can prove the theorem. So we were discussing the first part, how to convert a CFG to PDA. Okay. So if you are given a grammar with rules like this, like A goes to W, and with terminals like maybe one terminal, in this case A, then you build a PDA with basically three states: start state, loop state, and accept state. And if you are in the start state, you just push a dollar and the start symbol onto the stack. And every time you see a start symbol on top of the stack, you pop it and push one of its right hand sides of the rule, right? If you remember this example, like what did we do here? Here, we started with empty stack, then we pushed dollar, then we pushed S on top of the stack to generate this string. Basically, in this case, we are not generating, we are recognizing the string 0011. So whenever you have a variable on top of the stack, you pop it and push it with one of its right hand sides. Okay, but you push it in reverse order. Here, the rule is S goes to 0 as 1, but you should not push 0 first. You should push 1 first. You should push it as 1 as 0. Okay. Now, when you have a terminal symbol on top of the stack, you compare it with the next input symbol. If both of them match, you pop the terminal symbol from top of the stack and you proceed. If they don't match, you reject. Okay. Now, in this case, they match. So you popped it. Again, you got a non-terminal symbol on top of the stack. In this case, there is nothing to compare. You don't know what symbol this variable or non-terminal symbol will generate. Okay. So you need to pop it, push some rule, push some RHS again onto the stack. Again, we are applying the rule S goes to 0 as 1, right? And we are pushing 1 as 0 in that order. Now we got a terminal symbol on top of the stack. We compare it with the next input symbol, that is also 0. They match. So you pop it, you pop this top symbol. Now you again get S on top. Now you again apply a rule. In this case, you apply the rule S goes to epsilon. Okay. So you pop S and you push epsilon, that is equivalent to pushing nothing. Now you get a terminal symbol on top of the stack. You compare it with the next one, they match. Again, you get a terminal symbol on top of the stack. You compare it with next one, they match. Finally, you get a dollar. You pop it and you accept. Okay. So when you have a variable on top of the stack, you pop it and push one of its RHS. If you have a terminal symbol on top of the stack, you compare it with the next input symbol. If they match, you pop it. If they don't match, you reject it. That's the simple algorithm. Okay. And again, like I said, in this particular case, we are applying the right rule at each step, but we don't know what is the right rule, technically speaking. So we should try every rule, every possible rule. So basically, you try all the possible rules parallelly. Okay, if you are having an LHS, which is part of more than one rule, then you will have multiple right-hand sides. So you try to replace this LHS with all the possible right-hand sides and take different branches. So every possible right-hand side will be a new branch. So you try all the branches parallelly. Again, for each of those branches, you try all the branches parallelly, and so on. So if even one of these branches ends up in the accept state, the string is said to be accepted. Otherwise, it is rejected. Okay. So this is how you basically convert a grammar into a PDA. You start with the start state, you push dollar and S onto the stack. And then if you have a rule like A goes to W in the grammar, you add a rule, a transition rule in the PDA saying that epsilon comma A goes to W, which means you read nothing. You pop A if it is on top of the stack and you push one of its right hand sides. W is the right hand side. Okay. And so for each rule, you should add like that. And for each terminal symbol, you add this kind of a rule. If you are reading A and if you see A on top of the stack, you just pop it. That's it. So for each terminal symbol, you add this. If you're reading A and if A is not on top of the stack, then it will automatically be rejected because that case is undefined here. Okay. If I'm reading A and if I see B on top of the stack, I don't know what to do. So this machine will just reject it. So you need not separately write those cases. Only the cases which you listed, it will consider only those cases. All other cases it will reject. Okay. And here we looked at an example. If the grammar is S goes to 0, S1 or epsilon, we built a PDA. You start with Q start, you push dollar and epsilon. Now in this grammar, there are two rules and two terminals. Okay, first rule is S goes to 0, S1. Second rule is S goes to epsilon. For the first rule, S goes to 0, S1, you add a rule here as a transition rule. Epsilon, comma, S goes to 0, S1. Although the structure is same for the grammar rule and the epsilon and the transition in the PDA, the meanings are different. Here, S goes to 0, S1 means if you find a variable S in the string, you replace it with right hand side 0, S1. Here S goes to 0, S1 means if you find a variable S on top of the stack, you pop it and you push 0, S1. Okay, meanings are different. The structure is same. All right. So it is actually easy to just import the rule as it is, and you just put an epsilon before that. Okay. And similarly, for S goes to epsilon, grammar rule, you add transition rule, epsilon comma S goes to epsilon, which means you don't read any input, you just pop S. You don't push anything. Okay. And for each terminal, you add a rule like this. If I'm reading 0 and if I see 0 on top of the stack, pop it. And for 1, if I'm reading a 1, if I see 1 on top of the stack, pop it. That's it. So whatever number of rules you have, plus whatever number of terminals you have, so many total transition rules you will have. Okay. Finally, you will see a dollar on top of the stack. Just pop it and go to the accept state. Okay. And expanded version, this particular case, S goes to 0, S1 is a shorthand notation for this expanded version. So what are we actually doing? First, we are popping an S, pushing a 1. Then we are pushing S, then we are pushing 0. Okay, S goes to 0, S1, you're pushing 3 symbols, but you never push 3 symbols at a time. You push 1 symbol at a time. In the first step, you're popping something, you're pushing the first symbol, done. In the second and third steps and all the remaining steps, you push the remaining symbols. Okay. Now you try another example. So try to build a PDF for this CFG. let's draw. So we start with Q start. And then we go to Q loop. Here, what should I write? Epsilon comma epsilon goes to S dollar, which means you are pushing dollar first and then S. Okay, it's not always necessarily S dollar. Here S is the start symbol of the grammar. So in case some other symbol is used for the start symbol of the grammar, you should use that. Okay, don't just blindly use S dollar always. All right, and for Q loop, first we'll look at the rules. What is the first rule? S goes to ATB. So here, what should I write? Epsilon comma S goes to ATB. So we'll use the shorthand notation for now. Okay, then epsilon T. Second rule is this, no, S goes to B. So that same I should write here, S goes to B. Then T goes to TA. Then T goes to epsilon. Then, yeah, there are only two terminals, A and B. So for each of them, you write rules like this. That's it. Anything more? That's it. And finally, you go to accept state. Okay. And here, what should I write? Epsilon dollar goes to epsilon. Okay, that's it. It's quite easy. Converting CFG to PDA is quite easy. It's very mechanical. So now let's quickly look at the expanded version. So which of these rules can I expand? This one, S goes to ATB and T goes to TA. All other rules have only one symbol. Okay, so I'll just write here epsilon S goes to ATB. So first, say I'm coming to Q1. Here, what should I write? Epsilon S goes to B. Okay, and then right. In the second step, I'm not reading anything. I'm not popping anything. I'm only pushing the next symbol. Okay, and here epsilon goes to A. So I'm just pushing the third symbol. So this is done. Now this one also I should replace. Epsilon T goes to TA. So first let me make some space. What should I write here? Epsilon T goes to A. Okay, and here epsilon, you just push the next symbol, that is T. Okay, that's it. So this is the expanded version. Okay. Clear? Any doubts? So given any CFG, we can convert it to a PDA. That's it. So first part of the theorem is proved. Now let's move on to the second part of the theorem. So what is the second part of the theorem? Given a PDA, show how to construct a CFG that generates the same language as recognized as recognized by the PDA. Okay, so basically you need to convert PDA to CFG. We need to come up with a generic method for that. So before that, let's try to get the idea with an example. So let's consider the grammar. Say S goes to S1, S2, or SS, or epsilon. S1 goes to 0, S1, 1, or epsilon, and S2 goes to 0, S2, 1, or epsilon. Oh, sorry, 1, S2, 0, or epsilon. Can anyone tell me what is the language generated by this grammar? Okay, yeah. Any other answers? Yeah. Huh? Sorry? What do you mean 0, 1 power n? 0, 1 power n or 0, 1 whole power n? Okay, 0, 1 whole power n, 1, 0 whole power n. Is this 0 power n, 1 power n? 1 power 2n. Okay, 0 power n. Why? Oh, so you are saying you will have ones in between and zeros at the end. Like this, you are saying. Okay. Any other answers? Yeah.
Because we can take S goes to SS, now one of the S's. So it's 0 power n, 1 power n, and then 1 power m, 0 power n, right? Like it doesn't have to be, the first half and the second half don't have to be.
So what you are saying is 0 power n, 1 power n, and then 1 power m, 0 power m. Okay. Yeah. What were you saying? This whole star. Just a minute. Think. I'll come back in a minute. Okay, an easier way is to convert this grammar into a simplified version with only one variable. This grammar has 3 variables, right? You can actually convert it to a grammar with only one variable, with only S. Can anyone tell me that version? Hmm. Yeah. So this grammar is equivalent to S goes to 0S1 or 1S0 or SS or epsilon. Okay. Now can you tell me what is the language recognized by this grammar? Hmm? Yeah, that's it. Any string that has equal number of zeros and ones. 0, 1 union 1 0 whole star. No, because in this case you will only get pairs of 0 1 0 1 0 1 or 1 0 1 0 1 0. But we also need, it can be a sequence of zeros. A sequence of zeros followed by sequence of ones that will not be covered in 0 1 union 1 0 whole star. We can get, right, like earlier, like this is what 0 power n 1 power n, sequence of zeros followed by sequence of ones. So all possible cases, 0 power n 1 power n will also be covered, 1 power n 0 power n will also be covered, and intermittent zeros and ones will also be covered. Every possible case is covered. See, again, try to give a meaning to each symbol. Now, since I gave you the answer, okay, this grammar generates strings with equal number of zeros and ones, which means this start symbol represents such a string. Okay, because the start symbol generates the entire string, so the entire string can be represented by the start symbol. So if the start symbol represents such a string, now if I ask you to generate larger strings, keeping the condition intact, what will you do? Either you have 0 at the beginning and 1 at the end, or you have 1 at the beginning and 0 at the end, or you concatenate one proper string with another proper string. That's it. Very similar to matching parenthesis. If you already have a matching parenthesis, you generate larger matching parenthesis either by nesting this one inside a pair of parentheses or by concatenating this string with another proper string. Same thing here. If you already have a string with equal number of zeros and ones, if you want to generate a larger string, either you add a 0 and 1 at the beginning and the end, or a 1 and 0 at the beginning and the end, or you concatenate one proper string with another proper string. These are the only 3 ways in which you can generate larger strings. That's it. So you should give meaning to that variable. Then you will understand why we are writing this particular grammar. Right? So if I want equal number of zeros and ones, I need to sort of pair every 0 with 1. So every time I generate a 0, I generate a 1 also. But the order doesn't matter. So I will cover both the orders. That's all. Okay? All right. So you see, once you give a meaning, the grammar is very simple. But if you don't give meaning, it becomes very difficult. All right? Okay. So the language is the set of strings where each string has equal number of zeros and ones. Okay. Now, can anyone tell me how to build a PDA for this? What is the algorithm? How do you modify the stack based on the input symbol? Push when you see 0 and pop when you see. Okay, that's it. That will cover only 0 power and 1 power n kind of strings. That will cover only 0 power and 1 power n and 1 power and 0 power n. What about other kinds of strings? Interspersed zeros and ones. That's it. What if I am reading a 0 and 0 is on top of the stack? What should I do? If there is opposite symbol, I will pop. But if there is same symbol, then Yeah, but what should we push? What should we pop? That's what I'm asking. Okay, suppose you are not given this grammar. You are just given the language. Now I want PDA from the language so that I can convert this PDA to this grammar. Huh? PDA has only one stack. Okay, forget PDA. Just think of the logic. Don't worry about transitions. Just logic. Like in 0 power and 1 power n, what is the logic? Every time I get a 0, I push it onto the stack. The moment I get a 1, I pop a 0 from the stack. That's it. Forget PDA, transitions, all those things. Similarly, what is the logic here? In terms of stack transitions, stack manipulations. Okay, let's take an example. I don't know why CS and AI students take much more time. CS students take much more time than AI and ECE students. I don't understand. They gave much quicker answer. Suppose this is my string, 3 zeros, 3 ones, right? Now what should I do? First I'm getting a 0. What should I do? Push it. Okay. Now I'm getting a 1. What should I do? Pop it. Now I'm getting a 0. Push. Now I'm getting a 1. Pop. Now I'm getting a 1. Push. Now I'm getting a 0. Pop. Okay. Now tell me the algorithm. Suppose I give you a slightly different string. Okay. I'm getting a 0. I push. I get a 1. I pop. I get a 1. I pop. I'm getting a 0. I push. I get a 1. I pop. Okay. Now I'm getting a 1. I push. Now I'm getting a 1. What should I do? Huh? Push. Now I'm getting a 0. Pop. Now I'm getting a 0. Pop. So what to do now? Huh? You see, you should think in a discrete way, like clear-cut steps. These are the clear, clear-cut different scenarios, and in each scenario, I should do this. How many different scenarios are there? 4. What are those 4 scenarios? Yeah, if you are reading a 0 and if the top of the stack is 0, if you are reading a 0 and if the top of the stack is not 0, if you are reading a 1 and the top of the stack is 1, if you are reading a 1 and the top of the stack is not 1. Okay, I'm saying not 1, I'm not saying 0, because there can be more scenarios than just being 0. I'm reading a 1, top of the stack can be, when I'm saying not 1, it can be either 0 or it can be dollar or it can be empty. All these cases will be covered when I say not 1. But if I say 0, only that case will be covered. Okay, so I can actually compress all these cases and say not 1. That is much easier. Fine. So technically there are 4 scenarios. That's it. So if I'm seeing a 0, if I'm reading a 0 and I see 0 on top of the stack, what should I do? Push it. If I'm reading a 0 and I don't see a 0 on top of the stack, what should I do? Sorry. If I'm reading a 0 and if I see 1 on top of the stack, what should I do? Pop it. If I'm reading a 0 and I don't see 1 on top of the stack, what should I do? Push this 0. If I'm reading a 1 and I see a 0 on top of the stack, what should I do? Pop it. If I'm reading a 1 and I don't see 0 on top of the stack, push this 1. That's it. These 4 scenarios. Okay? Okay. So basically 4 steps or 4 cases. If the input is 0 and the top of the stack is 1, pop 1. Okay. If the input is 0 and the top of the stack is not 1, what should I do? Push 0. Okay. If the input is 1 and the top of the stack is 0, then what should I do? Pop 0. If the input is 1 and the top of the stack is not 0, then what should I do? Push 1. That's it. These are the 4 scenarios. This is clear? Quite simple. Okay. Let's move on. Now let's take an example. Say I start with a stack with dollar. I'm not starting with empty stack. I'm just starting with dollar. Okay. And suppose first of all, let's assume my input string is 00011. Right now, I'm just taking a string of the form 0 power n, 1 power n. I'll take another kind of string later, but let's assume this string. This is a valid string. Okay. Now I start with dollar and my read write head is on the first symbol, that is the first 0. What should I do? When I'm reading a 0, push it onto the stack. So the stack becomes $0. Now the read write head is on the second 0. What should I do? Push it onto the stack. Now my read write head is on the third 0. So my input symbol is 0 and 0 is on top of the stack. What should I do? Push this 0. Now my read write head is on the first one. So my input symbol is 1 and 0 is on top of the stack. What should I do? Pop this 0. Now the read write head is on the second one. The input is 1 and the top of the stack is 0. What should I do? Pop the 0. So I'm left with 1 0. Now the read write head is on the third one. What should I do? Pop the 0. And you come back to $. Okay. Now you see, as I am reading an input symbol, the or reducing. Okay, stack is either increasing or reducing. So if I try to graph the height of the stack, let's say this is 0, this is 1, 2, 3. Okay, so initially the height of the stack is 0. I'm not counting $. I'm just saying $. Doesn't count. Now it increases to 1, then 2, then 3, and again it starts. And so please excuse me. Okay, not bad. So now as you are reading a symbol, the stack is growing and reducing. If you notice, if the string is valid, okay, T U P. Okay. Now it is going from one state to another, so you can think of these as states of the stack. Okay. So from state P to state R, it is going on reading the input symbol 0. If it reads one more 0, it goes to T. If it reads one more 0, it goes to V. Now on reading 1, because it's 000 111, right? On reading a 1, the stack size is reducing. It is going from V to U. On reading another 1, it is going from U to S. And on reading another 1, it is going from S to Q. Okay. So this entire string 000 111 is taking the stack from state P to state Q. These states are different from the PDA states. This is just the stack state. If I give a name to the stack state. Okay. So 000 111 is taking me from state P to state Q. Okay. So I can assume that this string will be accepted or will be, yeah, this string will be recognized by the PDA. Okay. Now, similarly, if I assume only this to be my PDA, okay, this portion. For this portion of the PDA, which string is taking me from the start position to the end position? 0011. Okay. So this portion of the string will be accepted by that portion of the PDA. Okay. Other way of putting it is, if I have a grammar, now coming back to these rules. So let me call, okay. So suppose if you remember the previous example, say S goes to 0S1, and again if this S goes to 0S1, and say this S goes to epsilon, what we can say, this S, so let me call this S1. This S1 generates this entire string 0011. Okay. Let me call this one S2. This S2 generates only this portion of the string 01. If I call this S3, this portion generates only epsilon. Okay, so sub portions are generated by sub variables and larger portions are generated by larger variable. Okay, now similarly, so here I can call this will be my S1, this will generate the largest string. This I will call it sort of S2, this will generate a sub portion. Okay, and so on. Now I will, so this portion, like I said, this portion will be recognized by the entire PDA, and RS, whatever is there between RS, that will be recognized by the sub portion of the PDA. The other way of putting it is the largest variable in the grammar will generate this largest string 0000111, so that this particular string can be accepted by the largest PDA. Okay. Similarly, this smaller string 0011 will be generated by a smaller variable, so that it can be recognized by a smaller portion of the PDA. Okay, so I can name this portion from P to Q as, say, a variable called APQ. So this APQ will be mapping to, say, S1 in the previous grammar, the largest variable. This will be APQ. From P to Q, entire thing will be generated by this S. Okay, but between RS, that is like this S2, right? So what is happening? You have 0, and then you have ARS, and then you have 1. So that this entire thing is generated by APQ. Okay, this portion is generated by ARS variable. So this I can say, this is ARS is generating this portion. This portion is being generated by ARS variable, if there is a variable called ARS. Okay, and this entire portion is being generated by a variable called APQ. Okay, so I will map APQ to S1 and ARS to S2. Now I can also write it as, so if I map the rules, if you remember, what does the rule in terms of S say? S1 goes to 0, S2 1. Same thing if I convert to APQ ARS, it will be APQ goes to 0, ARS 1. Okay, so that's it. This is the main rule. This will capture, now this you can apply recursively and you can get all substrings. ARS can have a substring like ATU, but you don't need to write a separate rule for that. In that case, ARS will be APQ and ATU will be ARS, right? Like here, although I said this is S2 and this is S3, but from a relative perspective, this is my S1, then this is my S2. So I don't need to write separate rule for S2 and S3. The rule for S1 and S2 will cover the relation between S2 and S3 also. That's it. Unless if the nature of the relation is completely different, I don't need a separate rule. Maybe I'll need a separate rule to handle 1S0 situation. This is 0S1 situation. For 1S0, I will write a different rule. Okay. So basically, we are doing reverse engineering. All right. We are starting with a PDA. This PDA will accept those portions of the strings which will take the stack from its current state back to the same state. If the current state is 0, back to the same state, if it is 0, then that entire portion of the string which is taking the stack from this state to this state, that entire portion of the string will be accepted by the PDA. If the state of the stack is 1, and if some string takes the stack from 1 again back to state 1, you can think height 1, that portion of the string will be accepted by a sub portion of the PDA. Okay, that's it. Basically, wherever you start, you should get back to the same position. That portion of the string will be accepted by some portion of the PDA. That's all. You can't stop at a different level. Suppose if I start here. Suppose if I start here and I stop here, that will not be, both will not be at the same level, no? So this string 001 will not be accepted by any portion of the PDA. Okay, it is not taking back you to the same height. It is taking you to a different height. So that will not be accepted. Okay, some portion of the string on reading which the stack increases, decreases, and it goes back to the same position. Only that portion of the string can be captured in one variable. Okay, so that is the crux. Any doubts? This is basically height of the stack. And this is actually the input string. Okay, and this is variable mapping. And this is rule mapping. You see, I gave you the grammar just so that you will understand what we are doing. Technically, I should not give you the grammar. Technically, I should just give you the language and this example and some rules like variables like APQ, ARS, and rule like APQ goes to 0, ARS 1. But the reason I gave you the grammar is so that you can compare it with the grammar which we are generating or grammar which we are building, to compare that, okay, the grammar which we are building is mapping on to the actual grammar. That's all. So grammar is only, what do you say? It's just like a support. It's just for you to understand the example. Grammar I should not give you actually. Okay. So don't think first I have the grammar, hence I am building these variables. No. I am building the variables and grammar is independent. These variables are independent. I'm just showing you the variables which we are building. They are mapping on to the correct grammar. That's all. Okay. So for now, let's stop here. You need some time to sort of digest this, what I said. It is slightly complex for you to wrap your head around, but you need to reflect some time and then come back with doubts. Okay, we'll continue in the next class.